Bluetooth 6 introduced a game-changing feature, channel sounding. This technology enables precise, secure distance measurements using Bluetooth radios without requiring high power or line of sight to satellites. It's a breakthrough for applications like asset tracking, indoor positioning, and secure access control. But most resources on channel sounding feel more like marketing pitches, leaving engineers and curious minds with more questions than answers. That's why we're going deep into the weeds with this one. I'm Pat Deegan, and thanks to Nordic Semiconductor and the Element 14 community, I've got Nordic's nRF54L15 development kit, which has a chip fully equipped for Bluetooth 6 channel sounding, with complete documentation and sample code to make it work today. So welcome to the lab, where we'll dissect channel sounding from the ground up, from radio signals and protocol mechanics to working prototypes and real-world performance characterization. We'll break down how channel sounding can achieve centimeter-level accuracy, set up the nRF54L15 to run it, and test its performance in diverse scenarios. Plus, we'll try a proof-of-concept smart device to showcase a practical application. Whether you're an engineer designing wireless systems, a researcher exploring RF technologies, a curious tinkerer wanting to master channel sounding, this will equip you with the knowledge to understand the tech and make informed design decisions. So let's dive in and unravel the science and engineering behind channel sounding. It's going to be a fascinating journey. If you've made any IoT devices, you're surely familiar with Nordic chips. The nRF52 managed to be a capable and flexible little chip with support for all sorts of 2.4 GHz ISM band protocols, though I mostly use Bluetooth, and it was low power and pretty low cost. Then Nordic released the nRF53 series. With faster clocking and a dual core, it had a lot more punch for cases where you needed heavier crunching. This next generation, the nRF54L chips, are more like an extension of the 5.2, a plus version for similar use cases. The single Cortex M33 is clocked twice as fast as the older 5.2, and it, more importantly, manages to do its thing as an ultra-low power device, bringing serious energy savings to every aspect of the chip. A few of its features got my attention, namely, that ultra-low power processor and radio means smaller batteries or longer lifetime, and both of those will come in really handy. There's a RISC-V coprocessor that you can think of a bit like the RP2 PIO system. It's an independent little machine to handle time-critical tasks, custom protocols, and other useful jobs without requiring anything from the main processor. It has an 8-channel ADC that can be used so it's fast, 2 megasamples per second at 10 bits, or quite precise, making it up to 14 bits of resolution while still giving you over 30K SPS. But right now, what really got my juices flowing is that the nRF54L supports one of Bluetooth's coolest new features, that channel sounding. With 6.0, Bluetooth came out with a full system for precise and secure ranging, which is going to find a whole lot of applications when it starts making it into everyone's phone, because being able to determine with some precision a device's location, or at least how close it is to something of interest, is going to open up a bunch of more neat ambient computing use cases. We've already seen some of the possibilities of all that with GPS. Now, GPS lets you know where you are anywhere in the world, but only with the precision of some meters, and the real downside is higher power requirements plus the need to see the sky. You're not going to get much love trying to use GPS as a key fob in some indoor parking garage. Now, Bluetooth has long had presence detection abilities. You see an advertisement for a device, you know it's somewhere in the vicinity. Plus, by keeping an eye on RSSI, the strength of the received signal, you could also get an idea of distance. Frankly, this was awful. Not completely unusable. Years ago, I did design a key fob product using just that, but RSSI is so sensitive to everything, obstacles, the phone in your pocket rather than your hand, multipath effects, etc., that calling it inaccurate is an understatement. So how do you, in general, determine position with some precision? When thinking about ranging, figuring out how far something is, the first thing that comes to my mind is radar. Light, well, EM waves in general, have the nice property that they always travel at the same velocity in a given medium. This leads to some interesting consequences, but in terms of ranging, that's really quite practical. So the classic approach is to send a ping and just listen for how long it takes to bounce off a target and come back. From there, the math is really simple. Great, in theory. One problem is, no matter how good an object is at bouncing that signal back to you, the ping is affected by free space path loss the whole time it's traveling. If you tug on the EM field with some force, as that disturbance expands, the energy gets spread out on the area of a sphere that's growing at the speed of light. So wherever you are to see it, what you'll experience is a wave with energy that's gone down by the square of the distance, at best. So you can concentrate the waves in one direction, and you can boost the power, and you can use FMCW, sending continuous waves rather than short blips. It's all really interesting. And in fact, there's a fantastic series of videos by Marshall Bruner that includes tons of info and even Jupyter notebooks to play with. If you're curious about that, I'll link to it below somewhere. The point here is that radar is sweet, and depending on how you do it, can be extremely precise and deal with multi-target detection. But when you want to have distance measurements in some IoT product, say for some smartwatch, it's got three major problems. It requires line of sight. The first thing in the way is just going to bounce the signal back and hide everything that's behind it. It needs some pretty heavy-duty RF and processing, hence more power, to create and handle precise signals, usually in the tens of gigahertz. And you can know there are objects around, but you have no idea what's what. Is that my user or just a chair? I don't know. To get around all this and make distance sensing feasible on low-power devices that are already using radios on the ISM band, the Bluetooth SIG came up with a full specification for Bluetooth channel sounding that promises to be low power and give us distance measurements with centimeter-level accuracy. Okay, that sounds useful. Now, if you dig into the specification, you'll find that everything is there, but a whole lot of it is devoted to security. The goal is to both get the measurements and be able to trust them enough to do things like unlock your car or computer. That's interesting in itself, but here we'll assume all that is solid and stick to looking at the actual sounding process. To get to know channel sounding, let's start big picture. We'll peek at the nRF code samples later, but I set up a system using them and busted out the Spectrum analyzer to take a gander at radio. Now, all this Bluetooth is happening above 2.4 gigahertz, but my analyzer doesn't even go that far up. Still, we can use some RF magic to take a look anyway. If I just stick an antenna on the input of a little Morpheus, I can take whatever's coming in there and mix it with a frequency of my choice. So using 1400 megahertz as the local oscillator, everything coming in on the antenna will be shifted down by that amount. That means I can use the analyzer to sweep between 1 and 1.1 gigahertz, which it can do, and we'll actually be looking at everything between 2.4 and 2.5 gig. There's a lot going on in the band, but I attenuated everything down, and because the decay is so close by, only the Bluetooth from the device really shows up. Now with sounding running, you can just spot some quick blips, but if I turn on a trace with max hold and let it run for a while, a bunch of thin spikes start accumulating. Let it run long enough, and eventually you can see a big chunk of spectrum, almost 80 megahertz wide, is being used one tiny piece at a time. Now, Bluetooth Low Energy works by splitting up a portion of that license-free ISM band between 2402 and 2480 megahertz into 40 channels that are each 2 megahertz wide. Now, when devices are talking to each other, they hop around the channels continuously in some deterministic pattern. Now, 3 of these channels are special. They're reserved for advertisements, little packets that tell the world a BLE device is around somewhere. Now, these happen to be located at each end of the spectrum, plus a third one, right at 2026 megahertz, which, not coincidentally, is just where we see that notch in the middle that never received any power. So we've just seen how channel sounding can use all the regular BLE channels, but while it's doing distance estimation, it'll stay away from the advertisement channels to avoid interference. But what exactly is going on with all the blips? To figure that out, let's talk about the way it finds distances and have a look at the actual exchanges. There are actually 2 completely different ways channel sounding uses to do measurements. The first is analogous to radar, round trip time, or RTT. So with pulsed radar, you send some energy, it spends some time flying through the air, hits the targets, and starts being reflected back immediately. Comes back to you. Now, if you take careful note of the time of departure and then stop the timer when you first see it come back, you just subtract one from the other, and there you have it. That's twice the time of flight between the 2 objects. Speed of light, simple math, you're all set. Now, as mentioned, we have a problem because we're just not equipped to hear those minute echoes, and anyway, we'd want only the reflected signal from specific targets. I don't care about chairs, unless they're smart chairs. Anyway, to get around this, RTT uses a collaborative approach with both sides sending transmissions. I initiate things and send a ping to you, and then you, the reflector, actively send a pong back to me. Now, the trouble in this case is that you are going to take a little time to notice my ping and then to shoot out your pong. So the old time of arrival minus time departure trick includes more than time of flights. There's also some processing delay. And you can't ignore or fudge this. In 10 nanoseconds, light's going to travel like 3 meters. But this isn't radar. The devices are communicating and coordinating. So we can use this to our advantage. If the reflector pays attention to when it receives the ping and has agreed to send out a pong after a precise interlude, known as TIP1 in the spec, it has enough time to handle processing and setting up its radio, and then the initiator can account for that and just do subtractions to figure out the round trip time of flight. Cool. But there's a twist. You, my reflector friend, may say that you'll send out your reply after 10 microseconds. Okay. But do we really agree on what 10 US actually is? Variability in components, the temperature of the chips, the load capacitance on the crystal, and even its age are going to mess with the clock rates, and light travels so fast that it matters. So how can we account for that? Let's take a look at the on-air exchanges to show how that works. I created a little GNU radio flow graph to capture data on a bunch of Bluetooth channels from a Lime SDR sitting next to a DK that's acting as a reflector. I first started up capture and then plugged in the initiator a few meters away. Now, a few seconds later, I had gigs of RF data. To poke around in it, I like to use Inspectrum. Okay, with the file loaded up, we can see a few things. Now, if you don't know Inspectrum, the vertical axis is frequency, and you can scroll horizontally to move through time. Now, if you do know Inspectrum, you may notice some differences. I augmented it in a number of ways I find very useful, like, for example, seeing the actual frequency values here, and other things we'll see. I've submitted a pull request, but I'll link my forked version just in case. Looking at this, you can see I grabbed everything from 2.4 to 2464. So not every single Bluetooth channel, but 32 of the 40, so not too bad. Pretty patterns like this are fat Wi-Fi signals. Now this looks to be on channel 6. Brighter things mean higher power, so that's probably the laptop. What's of interest to us are smaller blips for Bluetooth low energy. Here's a strong one, so probably from our reflector. So looking at this doesn't tell us much, but what we can do is bring up a derived plot with a little tuner here. If I position the tuner on the center and tighten it up a little bit, check it out. The frequency is deviating, going up and down in a way that looks a lot like data. Okay, so BLE uses GFSK to encode bits. That's frequency shift keying. A slightly higher frequency is a 1, and a slightly lower is 0. Now the G is for Gaussian. To avoid spamming the band with a bunch of high frequencies from the sudden jumps, the shift is nice and smooth. And so that's why they look so rounded. So if I add another derived plot to just threshold the frequency, we can see 0, 1, 0, 1, 0, 1. The alternating 0, 1s at the front is a preamble, and since there are only 8, that tells us this is the 1 meg PHY rather than 2 meg, so each symbol lasts 1 microsecond. Let's see what this says by extracting the bits. So when enabling the cursors, you can just line things up so that you are defining where to interpret each symbol. In this case, yeah, each symbol is 1 microsecond long. If I grow the number of symbols here to grab all the bits, we could manually look at each one. However, something to know about Bluetooth. You've got a preamble of 0s and 1s that depends on what the access address, the next 4 bytes is. And that's great, and you could read those off. But after that, the bits get whitened, and data whitening makes sure that there's no long strings of 0s and 1s and stuff. But the point is you can't just read it off. So not to be done by hand. However, I can now use one of my other improvements to Inspectrum to feed them directly to an external program, a little Python script that'll de-whiten and try to interpret the bits. Okay. And here we go. It's on 2426. It's an advertisement packet. The name is my reflector, and you can even see that the service it's announcing is 18.5b. Look that up, and it's the ranging service. All right, we're in the right place. Great. Let's see what else we can find. Okay, here's a little transaction between two devices, and we can see that the initiator is connected because this is an LL-ENC response. So we're getting crypto set up. So from this point, encryption is going to munge everything. And anyway, this is all just regular BLE. Let's find some channel sounding. And here we go. There's some Wi-Fi going on at the same time, but this speckled starburst is Bluetooth channel sounding in all its glory. Pretty neat. Now, if you look closely, you can see they're all little exchanges. Lower power from the distant initiator and higher power responses from the reflector. And there are 3 shapes of signal that just keep repeating. So the first is this guy, a burst of what looks like a bit of data from the initiator with a response of similar data, but followed by a long steady tail indicating a fixed tone. Now, if I try to interpret this data with the script, that's because this is a pretty weird little packet. It's the CS sync, which has a few functions. So this guy has a preamble, an access address, and then a 4-bit trailer that depends on stuff before it, whatever. The fact it's 4 bits is kind of annoying because now everything that might come after is no longer aligned on byte boundaries. Anyway, here the initiator is just sending it off sans suffix and to start things off, and I can parse it with another program. Now, the response is almost the same, but you can see that long steady tail. There's like 80 microseconds of pure tone. Now if I parse that one, we can see it's a CS sync but with a tone, which is used for frequency offset measurement. Aha! Okay, now we finally see the answer to that twist from before. So the two sides agreed that a tone would be sent at exactly 2430 megahertz or whatever, but there's no gnome in these chips tuning an LC tank. It all starts out digital, so if the system clocks aren't in agreement, it's going to be measured by the initiator as a frequency with some offset. That offset, with math fully described in the spec, is used to figure out the delta in the clock rates to set expectations and correct for differences in timing. So there it is. That's always the first step, known as mode 0. So once that's done and the clocking delta can be compensated for, we can proceed with actual distance estimation. So speaking of that, here are some round trip time packets. You can recognize them because these are, again, CS sync packets. But you can see that there's no tone and they both have some data after the trailer. In fact, they have 64 bits of pseudo-random data appended to them because that's what I asked for in the config. Those random bits are generated using a deterministic random bit generator, so they can guard against spoofing in replay. So this is the ping pong for RT. If you look at when the initiator side ended compared to when the reflector started, it's about 65 microseconds. The spec defines allowable values for the delay, and here it looks to have been 60 US, so wait, was it really traveling for 5 microseconds? That would be like a mile. No, actually, there's a ramp down period to allow the airwaves to cool off. So the time of flight was actually much closer to like 10 nanoseconds in this case, and I can't measure it with these crude tools. Okay, so that's the RTT measurement and how it's done. You can see them pop up regularly in here, and they are the Mode 1 exchanges. So what are all the other sparkles in there? Well, we finally meet the mysterious Mode 2. So the RTT measurements are cool, but it's really hard to get something accurate with low power and low cost receivers, just because light travels so fast. But there's another property of EM waves we can use: phase. Now, even if you can measure the phase, and even if I tell you that I started sending at 0 degrees, and you start receiving it rotated by some amount, say you're standing there at the 10 line there, you still don't know how far I am because you don't know how many full cycles it took, times it went around full circle, before arriving. All you know is the modulo. But what if I send you 2 different frequencies? Or 5? Since all light travels at the same speed, if you're sending a higher frequency, that means it oscillates more often for a given step forward. This sweet property means that signals of different frequency will arrive at the same spot in different positions in their rotation. As you get further, the phase spreads out more and more. So as long as you can measure that, you'd be in business. In theory, you only need to do this with 2 different frequencies to calculate the distance. The main problem is that phase ambiguity will come into play once you're far enough that the difference is more than a full rotation. You're back to modulo. When you have a large gap in frequency, this will happen faster, so you don't get much range, like 4 meters before you can tell any more between the first and last Bluetooth channel. Frequencies that are close together diverge more slowly, so you could get hundreds of meters before this is a problem, but it means that the difference close in is tiny and hard to detect. So channel sounding hops around and does a bunch of measurements, hopping around on many channels, which is what we're seeing in the spectrum there. So that's what all these extra sparkles are. Mode 2 phase-based ranging, sending pure tones and hopping around from channel to channel. Notice that it goes both ways. The initiator sends a tone, then the reflector sends back the same, so both sides are collecting data. At the end of all that, you'll find these bursts, like 2 kilobytes of data from the reflector back to the initiator, where it's reporting all the good stuff it's collected. Neat. So why bother with 2 completely different methods? Well, choice is nice. RTT is simple and fast and basically has the same range as your radio. PBR is more involved, but can be very precise. More importantly, the redundancy helps with security. It's pretty tough to harden a pure tone against attack. So you do both, and if phase says you're 1 meter out, but RTT reports you 40 meters away, something is off. How about we not unlock the Ferrari just yet? So we've done the channel sounding on the air. Now, what happens to all the data collected? The Bluetooth SIG was pretty wise, I think, in how they set this up. You have a bunch of parameters you can tweak to customize your sounding, like which methods to use, which channels, how many repetitions, how many antennas, stuff like that. But once the data is collected, the measurements get bubbled up and the actual algorithm used to estimate the distance is left as an exercise for the reader. Now what I mean is they haven't mandated some particular method of determining distances. That leaves a ton of room for selecting the right trade-offs for your particular circumstances, and for both hardware and software companies to offer distance estimation algorithms as IP, as a value add in their chips or SDK or standalone or whatever. In the case of the initiator code I was using, that was the Nordic Channel Sounding RAS initiator from the sample. Now in that single file of code, you'll find everything needed to run an initiator. There's a callback that's triggered whenever data is ready, ranging data callback, which just grabs the data and calls a function csdecalc. Now wonderfully, the source code for that is available in the nRF Bluetooth subsystem. I'll show it here on GitHub, but it's all installed as part of the SDK. We won't go deep on the algorithms, but what I want to show you is the kind of data they're processing. One of the calculations gets the distance from RTT, and that is just using an accumulated measurement of time. Okay, cool, nice and simple. For the phase stuff, it skips any tones that got interfered with and then uses K's phase estimator, a method for estimating the phase advance from one sample to the next. Look. It's just taking IQ data, summing all the I's and Q's, and then using the arctan to find the angle of that triangle, i.e. how fast the phase is changing from frequency to frequency. The further out you are, the bigger the slope of that triangle. By the way, if all this IQ stuff is new to you, it's much cooler and actually simpler than you might assume. I think the best intro I've seen is the SDR video series by Michael Awesomest, the guy who made the HackRF. I'll drop a link to that. The last method of estimating distances also uses the IQ stuff, and it's doing inverse Fourier transform things. Fascinating, but yeah, let's not get into that. The point is that after each little ranging dance, the Nordic initiator code is getting estimates using 2 sets of data and 3 different methods. So wow, now we know a whole lot about channel sounding, but does it give good results? And if so, how can you put it to work and what can you do with it? The first thing I did was use the Nordic initiator and reflector samples just to see it working. Getting basic sounding going was easy, but the results seemed a little high and up close and kind of jittery. But this is a tight and cluttered environment with signals bouncing everywhere, so to give it a chance at working in a best case scenario, I wanted some data points from the closest I could get to measurements in free space. The ideal would be a direct line of sight, nothing in the near field to interfere with radio waves, not even the ground. So I set things up to spit out data as it was received and allow me to use a button to switch between doing runs with a little averaging window that only accepted high quality reports and another mode with no filtering, no averaging, nothing but the raw calculated distance estimates using the IFFT, the Fourier, phase slope, and round trip time just as they came in. Now to get mobile, we need a way to power the reflector. 2 things make this easy. The DK has a jumper that you can use to monitor current to the chip, and you can just feed power through there by connecting between ground and the center pin. The other thing is that the nRF54L are forgiving in terms of voltage, so anything between 1.8 and 3v3 should be fine. I just hacked some random AA battery holders I had lying around to allow me to use just 2 in series rather than 3, which gives us about 2.7 volts here. Now I bore with someone's clothesline and risked everything by sending out a DK with that AA power pack taped to its back out to act as the reflector dangling in the air. For the initiator, I needed a way to get the readings. There's a little open source app called Serial USB Terminal by K. Moritz that I like a lot. It lets you both power USB devices and access the serial terminal and log everything to files. Perfect. I use it every time I need to go on the road and want to know what's happening with some board I'm working on or to collect data like here. It's a lot more practical than lugging a laptop. With the DK, there are actually 2 serial ports. The Zephyr console log shows up on port 2, so you select that and you're good to go. So I pushed the DK out to 3 locations and collected some readings from distances which I figured were about 5, 10, and 15 meters-ish. The point here was just to see how things would perform and how consistent or jittery the readings might be. This guy has got that guy in his sights. That is approximately 15 meters. Looking at the data, you notice a few things. First off, there are a lot more samples to play with in the raw run than the high-quality filtered, which is kind of expected. Now, comparing the distance estimations, round trip time almost always works. IFFT always seems to report the shortest estimate, and it's also the most sensitive to disturbances, having the highest failure rate. And then the phase slope method is a lot more finicky than RTT, failing between 30 and 70% of the time, still better than IFFT, but more important, it's always reporting a distance that's 20 or 30% greater than the other two, which do match up pretty well. Okay, so RTT and inverse FFT agree, but the way this experiment was set up doesn't actually tell us if they are correct. For that, I need to have a better idea of how far out I really am while taking readings. Now, I started out with the sample code, but at some point you want to get serious and start coding up your own. Now, we've talked a lot about the channel sounding, but how do you start working with this particular chip? The nRF Connect desktop is perfect for getting started with all the Nordic semi chips. You can set up your device and program it with a few samples. There are links to the crazy awesome documentation. There's a way to install Visual Studio integrations, which I didn't try and will never use, but may make things easier if that's your thing. And you can interact with the board in a few ways. You may have noticed how simple the DK PCB is. Compared to the kits from older boards, it's really streamlined, and part of the reason is that rather than use a million jumpers, you configure it using the desktop app. It's kind of cool and probably reduces the price, but I'm not sure what I think of this because it turns things like the VDD.io into mystery meat. There's no way to tell what it's set to by looking at the board, and I almost got bit by that. I don't know how much that matters. What do you think? Anyway, the system is cool, but the number of samples is limited compared to the ton available in the actual SDK. Now, there are three things to note about coding real applications for these chips. The SDK is built atop Zephyr, an open-source, real-time operating system designed for embedded devices. Now, I love Zephyr. It's scalable, modular, supports tons of hardware, and it's open. But if you're new to it and just trying to get your Hello World Blinky LED going, it can feel like trying to sew with a sledgehammer. It's big, it uses device tree overlays and magic cake config files for configuration. The flexibility comes at the cost of arcane abstraction layers. Not gonna lie, is a steep learning curve. If you're building a real product and want to have code you can extend or port to other platforms easily, it is excellent. But you will have to put some work into grokking it. The second thing is about support. The documentation is excellent. The Nordic Developer Academy is really something. But sometimes you're stuck with a question. I'm the kind of guy who'll dig into the source and figure it out, and Nordic contributes a ton of open source. But if you look at the application stack, there's one layer there, right between the hardware and everything else, that is a binary blob. The soft device controller is a complete mystery to you and I. Now, you interact with it, but sometimes it misbehaves or just gives you some really cryptic error message. Because it's proprietary and hidden, that's it, you're cooked. Thankfully, there is the dev zone for free support. Now, I've relied on it periodically for years and have gotten some results. It usually takes a couple of days to get a response, and they tend to come back to you with a question or a simple "did you try this?" which is the first thing you tried. So just be very complete and specific in your posts, and eventually it'll work out. And finally, there are samples for everything, like everything. But a lot of them look like the channel sounding samples. One big file that does all the work, meaning boilerplate setup, basic interactions, application logic. It's a lot of spaghetti and hard-coded to one specific use case. Fine for a demo, but not for real-world code. So the first thing I did was untangle the spaghetti to separate out the low-level setups and callbacks from the application logic and stick it into a library we could reuse without cutting and pasting all that stuff into every single program. Then I got rid of the notion that we'd only be connecting to a single device and stuff like that, and basically made all the function calls from the sample into a usable API. Now, distinct from that, but still in pure C, I made a few utility functions, and then on top of that, I created a C++ channel sounding class that makes it all pretty usable and easy to understand, in my opinion, and lets your app focus on its actual job. I'll have a link to all that code here. So I created a little program using all that to simply connect to one reflector and dump readings, then made a plan to go and capture better data. So I've come to the park, try to get some data in a nice open space. Popular day over here though. 5.022. That's good enough with the cardboard a little bit behind. Now, my cheapo laser distance finder had trouble handheld and outside beyond about 7 meters, so I just planted a flag every 5 meters. I tried to be somewhat precise, but will admit the positions were a bit rough.
Right, I've got my flags everywhere, all down this line, and now it's time to set up the electronics.
I got some help from a little tree to hold the reflector at my 0 point and started collecting. Data, data, data. It wasn't completely smooth. As I got out further, results started getting pretty sensitive to how I was holding the initiator. Somehow it's better when I raise it up here. 34.398254. And here, RTT is dead. Now I read that wrong there. RTT was still doing okay, but phase and IFFT were quite finicky. And when I'd lose the BLE connection, it wasn't always easy to get back in.
No, having trouble connecting from 35 meters.
The connection worked, but the step where you set up security on a link is sensitive to RF noise and disturbances. Still, I did manage to get readings out to the end of my line of flags there.
45 meters, well, thereabouts. I think my errors accumulated here. It seems to be more like 43.5. Maybe 44.
At just 5 meters, the results aren't bad, but the phase slope measurement has a full meter extra, and I think the winner here is IFFT. Now, as I moved away, the phase slope was usually greater, but kind of stabilized around reading 2 meters extra. The RTT measurements have a lot of wiggle, but they do average out quite nicely. At 20 meters, that's less than 1% failure rate, and it's pretty spot on. 25 looks pretty good. At 30, not great agreement. 35 came out really nice. And 40, even better. And all the way out to 45, things are still pretty decent. Okay, so the conclusion is that with this setup at least, we're not talking about 20 centimeter precision. Now, my waypoints weren't necessarily perfectly positioned, but looking at the summary of the results, if it was a position error or there was some systematic error, as I moved, say, 4.5 meters back, then they would all increase by that amount or something proportional. Instead, if you look at the delta columns, that's how much I moved from the position on the row above, and the difference between those deltas in the 3 final columns is just spread out everywhere. It looks like jitter and the distance estimations themselves on the order of 60 to 120 centimeters. So if you're looking for a very precise estimate, you're going to have to look into better antennas, or probably more importantly, getting antenna diversity by sticking 2 on each device, ideally getting both spatial and polarization diversity, and then leveraging that in the algorithm used to determine the distance. Still, this single PCB antenna seemed good enough for many applications. Distance is cool and useful, but what if we tried to get an actual position in space? Well, with one value, we'd know we're somewhere around the reflector on a big circle with that radius. Officially, to get a position using distances, we need trilateration, to use the measurements from 3 fixed points. Now, the reason it's 3 rather than just 2 is that unless the distances are exactly equal, in which case the 2 circles you're on intersect at just 1 point, most of the time the circles will touch in 2 places, so it would take a 3rd circle to choose between the 2 possibilities. But to minimize the requirements, you can limit the playing field, say by assuming the 2 fixed points are in the corners of a box, or that you'll always be on one side of the line between them. Now, to try that out, I whipped up some code that would get distance estimates from 2 reflectors, A and B, and then do a little math to figure out where the circles intersect. That meant handling 2 things: getting channel sounding going with 2 reflectors and fixing the distance between them. I set it to 20 meters between A and B, and putting in some smarts to deal with all the jiggle we saw in the distance estimates. That's because, say both estimates come up a little short, then the circles won't intersect at all and the math will conk out. For that, I went conservative and just assumed a measurement might be within plus or minus 50 centimeters, which basically defines a band rather than a circle in which you might be located. I tried getting sounding data from 2 reflectors simultaneously, but haven't got that to work yet. I think the sounding sequences might have been stepping on each other's toes. Even connecting to both and then sounding one, then the other caused problems, with the first reflector always failing after that first single success at the beginning. So at this point, there's still an unresolved thread about it in the Nordic Dev Zone support thing, but I want to do this experiment right now. So I just went the dumb brute force way, connecting to A, getting a few quick raw unfiltered measurements, disconnecting, connecting to B, getting a few measurements, disconnect, and just repeat. It's slower owing to the bring up and tear down of the links, but it seemed to work, and the other details can be sorted out later. So time to take the show on the road.
All right, made it to a second, nicer park. And this time what we're going to do is try and get some positioning information. Instead of using 1 reflector, we'll use 2 at each corner of a virtual square. Let's do it. All right, so now I'm at corner A and I'm collecting some data. I'm going to walk to that other corner, I don't know, maybe 20 meters away. Next corner, down to the B corner, and then I'll do a diagonal, and we'll slowly do that.
Well, that was the original plan, and it did work out pretty well at the start
of the square, right about in the middle, which should be about here. Try to collect some data. So I'm holding this up high because I keep losing tracking. It's kind of weird, but okay, I got some position here. Now it believes I am at 10 meters and 12. I think this is working.
Here's the raw data collected, and when I replay it slowly, you can see the data updating from one reflector and then the other. Focusing in on our play area and the points as determined by the initiator, here I am walking up from A, then heading towards B around the top of the square. Though I wasn't as far out as for my tests in the first part, the fact that I had to disconnect, reconnect all the time meant having to bring up security and everything over and over, and made it a bit more finicky. Wound up breaking with the plan and walking back at some point when I was having trouble reconnecting, so I went to the center there.
All right, I lost my connection to A here and I couldn't reconnect, so I had to move to the center for a little while. But now, let's see. Yeah, now it's working again. So I'm going to move back to that corner.
So I went back to the top B corner, then made my way down to the B reflector about 20 meters out from A.
All right, I'm in the B corner here, and I'm reading 19.4 and 2.6. So that does seem to work. I'm now going to walk towards A again.
And finally walk back from B to A along the line at the bottom. Here, nice and close, the data is quite consistent.
All right, so I'm calling this test a success. We'll see what the data says back at the lab, but for right now, I'm going to enjoy some time in the park.
Yes, I'd say it's definitely a useful way of estimating position. Now, augmenting my basic test with persistent connections would allow updates to come in fast enough to apply some smoothing while still closely tracking position, and adding a third reflector would get rid of the restriction of staying on one side of the AB line. All the code is online and linked below, and I'll link to the DevZone thread as well so you can see where that got along. All right, we got distance, we got position. Let's see a way this could be used in something real. This is a little board I whipped up with an nRF54L15, basically blind. Now, I recently created KiCad Unlocked, a full KiCad course, and though the focus is maximizing KiCad proficiency, I wanted to demonstrate everything doing a full walkthrough using a non-trivial example. Now, if you want to learn all the techniques I've accumulated over the years and see the walkthrough, check out the course. But the point is, since I'd been reading up on the nRF54L for this video, I came up with this guy, the teletoggle, which is built around the chip. Now, the fact that I got version 1.0 up and running before I'd even seen the nRF54L15 is a testament to the quality of the documentation and how easy it is to use. Now, this board has 4 opto-isolated inputs and 2 bistable relays that can switch 120 volts AC. So how about we make a smart lock? I'll use a 12-volt parser lock switch and define 2 zones: a proximity, inside which we'll switch on the lamp in the mains, and a smaller authorized zone, inside which will allow a switch to open the lock. Now, code-wise, it's nothing complicated. I just set up channel sounding like before and feed the distance to a state machine that defines the zones with a little hysteresis that handles the lamp and lets you operate the lock if you're in the authorized zone. So let me set that up and show you. I've got the teletoggle here, and one of the inputs is monitoring this switch. So that's just some industrial type switch thing. The outputs, the relays, one of the relays is actually taking about 10 volts from up there and piping it into this guy on demand. That is the lock. So the lock is there. It's going through this relay, this guy. This other relay is hot. It's actually controlling this hacked up power bar. So that's great. Now everything is running on this through a coin cell, and so it's all pretty much standalone and wonderful. So what we're going to do is take a look at what happens. See that red light? It means I'm out of proximity zone. So let's bring it a little closer and see what happens. I set up the teletoggle as the initiator, and this time I powered the reflector using the phone, and you can see that as I get close, the lamp turns on and the LED on the PCB is flashing yellow. Now, if I leave the reflector over there and press this button, nothing happens. But from here, however, let's press the button. Oh, many zones work nicely. Here I am in the yellow zone. Can't switch, but the light's on. If I bring this in a little closer, now suddenly, oh yeah. The neat thing is I got the board done over a weekend and the code in less than a day. Well, thanks to the work I put into the library. Now this one's a pretty simple application, but there's huge potential with channel sounding, and it's going to get really interesting once all the phones have it available. It's a good time to start thinking about leveraging it. If you have any cool ideas of how you'd use it, let me know. Okay, wow, we've covered a lot, from airwaves to application. So another thank you to the Element 14 community and Nordic Semiconductor for inviting me to do this. I hope you found it as interesting as I. Now, if you want to get started, grab a couple of the development kits and follow the quick start. Or you can go deeper with Nordic's Express course. Let me know if you have any questions or would like to see some deep dives on some other topics, and happy sounding. Thanks for watching. Cheers.